Okay, hello. This video will be very quick. We'll talk about the rest part in chapter 9, and specifically, it's about calorimetry. And although it has the topic of calorimetry, but actually just another form of a calculation in chemical energy. Okay, so um, let's just take a look in the content and the example problem very quickly. So basically, calorimetry is that you can measure the heat you absorbs inside of the system, and you can measure the temperature change in the system. And by using this equation over here, what is the equation? The energy change will equals to specific energy heat capacity multiply by the mass and multiply by the temperature change. Or in a familiar case for our experience is use the molar heat capacity, which means we calculate the energy change by there's more there are n moles of substance in your systems and there is a change in temperature. Okay, so we want to know about when 1 degree Celsius change in temperature or 1 Kelvin change in temperature, how many change would it be in enthalpy? So there will be a specific heat capacity. Sorry, there will be a molar heat capacity with the unit in joule over degree Celsius dot mole or joule over Kelvin multiplied by mole. Okay, it can be put like this. Okay, now let's go to the next part. When it comes to energy change, like enthalpy change or internal energy change, what we care about is what is this relationship with the temperature change. Is that clear? Because from the previous example from the last part, we talk about Q, W, E, and enthalpy. This is we know that in ideal gas is only related to temperature change. Okay, so first of all, if you're a Taiwanese student, I think you'll be very familiar with the part that the change in energy is usually used enthalpy as the measurement. Okay, so notice another thing that when we talk about this kind of problems, when you're calculating this part of problems, it usually has the assumption that pressure is constant. Okay, when it talks about heat capacity. Okay, now. We know, uh, we can know from the measurements to find out the enthalpy change in the system. And next is, what is the internal energy change? Okay, so for liquid, okay, this is the easy part because, when we add a heat or make the temperature rise in the system of liquid, it will not make the volume change that much. Well, it will have a little bit change, but it's not significant to have a work energy inside of the system. So basically, we consider that there is no energy change inside of the system. Okay, but so in this part, we can easily say that there is no PV work because from the definition delta H will equals to delta E plus delta PV. Okay. All right. So we know there is no volume change, and when there's no volume change, there will be no work energy. So enthalpy will equals to the internal energy. But for gases, we know that when in constant pressure, what will happen? Oh shit! No. In constant pressure, okay. Okay, when the pressure is a constant over here. You rise the in temperature, what causes an increase in the volume. So we know from the previous chapter, the content, when the system has an expansion, it means that the system had did some work on the surrounding, so the work energy will decrease. Okay, so again, the energy in the form of work will decrease because the system did some work on the surrounding. So in this part, for gases, the enthalpy should not equal to the internal energy usually. But so let's take a look over here. This is kind of a review. H equals to E plus PV. And P is a constant over here. Okay, since E is a constant over here, P is a constant over here, so this part can be E minus W. But why? We already know that work equals to P delta V and add a negative sign over here. So it will comes to the same result as the PPT slide has written down on here. Okay, so we know from the previous part when there is a volume change in the system, we should consider the work energy so that we can calculate the correct value in enthalpy and the internal energy. So let's take a look at the example problem over here. Okay, when 2 moles of SO2 reacts completely with 1 mole of oxygen to form 2 moles of SO3, sulfur trioxide, at 25 degrees Celsius. Okay, at 25 degrees Celsius means that the T will not change. Or at least that the statement is like this. And the constant pressure of 1 atm. Okay, now we know that P is constant. 2. Okay, 198 kilojoules of energy is released as heat. Okay, calculate the enthalpy and internal energy change for this process. Okay, now from this part, we already know that the enthalpy change will be negative 198 kilojoules. Okay, because when it comes to chemical energy, the first thing we will use is always to describe heat is always enthalpy. Okay, not internal energy, it's enthalpy. Okay, so let's take a look at the ideal gas equation over here. Okay, PV equals to nRT. Okay, we know from here that T is a constant, temperature is a constant, so this part you don't need to consider about T. And now P is a constant as well. Okay, so let's take a look over here. In this part of the calculations, we can see that, okay, N is proportional to 成正比 with the volume. Okay, from the previous section, I have told you that if there is a volume change, there should be a working energy, no matter it's negative or positive. Okay, so now there is a change in mole. You can be very clear over here. From the initial stage, there will be 2 moles of SO2, 1 mole of oxygen. And in the final state, it should be 2 moles of SO3. In this part, we have 3 moles of gas, and there have 2 moles of gas over here. So there's a decreasement in the moles of gas. So when it comes to a decreasement of a mole of gas, there should be a decreasement in volume as well. Okay, so now we know something. Okay, since the work, okay, since the volume is decreased, so we can know that the system will have an increment in working energy. Okay, okay, that's fine. Okay, so now let's take a look. We want to calculate what is W. So in over here again, we know that internal energy should be enthalpy plus delta W, or you can just write it down as W. That's fine. Okay, okay. So now we know that the pressure will not change and temperature will not change. So P delta V will equals to delta N dot R dot T over here like this. Okay, so this is, you can calculate the work energy from here. Okay, and note that the value should be positive. Okay, is that fine? Okay, so like delta N should be 2 minus 3 dot, sorry, 8.314 times by no temperature change. So it is 298 Kelvin over here. Okay, so after we calculate this, this is negative 2.84. Sorry, in this part is 2.84, negative 2.84 for 48 joules. Okay, so the negative PV, we know that W should equals to negative P delta V. And since the P delta V is negative 2.84, so negative P delta V should be 2.48. Sorry, I think I read the number incorrectly. So I think so. So you should read the number over here. Sorry. Okay, so now you can calculate the internal energy change simply by using QP, or you can say that's enthalpy plus the working energy, energy in a working form, and simply get the answer over here. Okay, I'll leave it to you. Okay, another question. When it comes to there's a phase transformation, like liquid vaporize into gaseous state, and the important part is that there should be a phase transformation heat over here. So let's take a look at this problem. Okay, notice that I didn't calculate the enthalpy. Sorry, I didn't calculate the entropy, and I did not. Yes, I did not calculate entropy yet because the entropy belongs in chapter 10, and I will cover it in the next video. Okay, so now the heat capacity of H2O is 75.3 joule over mole K. Heat capacity of H2O in gaseous state is 25 joule mole K. Okay, now we can, okay, here's a thing that worth notice again. We know that with a stronger internal interactions, the heat capacity will be larger. We have talked about that because like monoatomic has a heat capacity in constant pressure is 3 over 2 R, and diatomic CV will equals to 5 over 2 R. So because there has a more complicated interaction inside the molecule, so the heat capacity will be larger. But in this part, the liquid water should have a larger heat capacity because the molecule is more near each other than the gaseous state. Okay, it's reasonable. Like maybe this is like water, and this is gas. The interaction in a water molecule is more denser than the interaction inside of water gas. Okay, so let's take a look over here. Okay, the heat vaporization of H2O is 40.7 multiplied by 10 to the power of 3 joule over mole at 100 degree Celsius. For the change of 1 mole of H2O at 90 degrees Celsius to 100 degrees Celsius under 1 atm, calculate the energy change, which is internal energy, enthalpy, Q, and W. Let's just focus on this now. Okay, so because that this is a constant pressure, so that now the Q will be QP and equals to the enthalpy. Okay, so this is easy. So basically this is just using NCP times multiplied by delta T over here. Okay, like I just say like, oh my God. Okay. Okay, there's one more of substance over here. So we have to calculate in each section, which is when you're still a liquid and when you are having phase transformation at 100 degrees Celsius. Okay, and then third part is when you're increasing in temperature from 100 degree as gas to 115 degree as all right, like this. So okay, so in this part we will have to calculate three sections of heat transformation. Okay, so first part is from 90 to 100. It should have 10 degrees Celsius of change, and when you're at 100 degrees Celsius, you are transforming your state from liquid to gaseous. So the question has stated that you only have 1 mole of over here, and for 1 mole of water to vaporize, it requires 40.7 multiplied by 3 to the power of 10 to the power of 3 joules over here. Okay, the last part is you add some temperature when you're in a gaseous state. So Q, heat, and enthalpy should be calculated very easily over here. Okay, so now let's take a look at the working part. Okay, so like this. Basically, if this is a system and this is water over here, okay, and when you vaporize, you turn into molecules of gas molecule over here. So you will make this system extend. Why? This is reasonable. Imagine this. There's a cup of water inside of the cup, and the volume inside of the cup is visible. You can see it. But when it becomes into water, you know that the volume will expand very dramatically because the distance between the molecule is very different between water, liquid water, and gaseous water. So inevitably, there will be a gas expansion, volume expansion in the phase transformation. So because there is a phase transformation and the volume expansion, so we can expect it that the energy in a working form should have a sign of negative. OK，用中文讲一次，就是因为我们蒸发了，我们蒸发了之后呢，这个东西，这个你会导致你的系统的这个体积扩增。那你体积扩增的话，就表示说，哎，你对你外界做功了，你对外界做功的话，那你自己就会少了一些以功存在的能量。OK，好，没问题。OK，so when it comes to calculating the working energy, you always have to know what is the change in volume. That is what matters, right? Okay, so the pressure is always 1 atm. So in when we are holding in the temperature of 100 degrees Celsius, okay, what should happen? Originally, you come from 100 degree H2O. Okay, we expect sorry, let's keep going. And you go to 100 degree H2O in gaseous state, and there is a volume, and you can calculate this by ideal gas equation. Oh, sorry. Okay, we pretended that this volume is so small comparing to the gaseous state, small. So we can say that the volume expansion should equal to the gas volume of the gas. Okay, so let's take a look over here. A V should equal to 1 multiplied by the gas constant and the temperature over here. Okay, so it can easily to be calculated. Okay, notice the unit. You need to be calculating this very carefully. Okay, so we choose the unit as liter, so we will use the gas constant as 0.082. Okay, so now we know the volume change, so we can calculate the W change in the process of vaporization. Okay, so basically, you just use negative PV, then you can calculate the work change, the energy change in the form of work. Okay, so basically, because it's expansion, as I mentioned, so the value should be negative. You can read it by yourself. Okay, so okay, let's. Oh, I think I missed some part in this slide, didn't I? Oh, I missed something inside of this. Okay, let's wait for a second. I have to check my notes. Sorry, I apologize because I think I missed something in this. Oh, really? I missed something. Okay, in this part you have to write. I have to write down on this PPT slide now. My apologies because I forgot to write something down. Okay, now we have to calculate the W from 100 degrees Celsius to 150 degrees Celsius. Okay, now, sorry, if you don't want to see the calculation over here, you can skip it to the last one. You can skip the process and just read the PPT. Okay, so like uh, when you're adding some temperature in the gaseous state, you will expect there be a expansion, more expansion in the process. So, but the the pressure is a constant, which is 1 atm. So we can expect that the working energy change should be negative 1 multiplied by the volume change, which is expanding. Okay, now we also know that PV equals to nRT, and this one two will not change, and this will not change either. So the volume will be proportional to the temperature change. So this part we can write like negative 1 times R times the delta in T is 15, 100 to 150. Okay, so I think this is very simple over here. Okay, so the calculation should be very easy. It's like this. Oh, sorry. Okay, I'll leave the calculations to you, and this will equals to 1.25 multiplied by 10 to the 2 power of 2 joules. Okay, so okay, did I miss anything over here? Okay, so basically, the the total working energy over here should equals to this plus this over here. So we have calculated the whole process of work in energy change, which comes from the vaporizations process in the expanding over here process over here. Okay, so for the whole process is can be calculated by heat plus W. So we already calculate the heat plus heat over here. Total heat is over here, and the working part is over here. My apologies because I forgot to I forgot to scan this part. My apologies. Okay, so the final answer of internal energy change is over here. 诶，我真的没有放，我天哪，真的是疏失。Okay, okay. The next part is standard enthalpy formations. Okay, I think I should leave this to you because I think this is the PPT slide will be very easy to read. So I will skip this part and talk about one question, just one question. So basically, if the problem give you each each substance in the reactants or in the products. And it gives you the enthalpy of the formation of each substance of the reactants and the products. You can just easily calculate it, the whole reactions delta H, which is the enthalpy change inside of this. So basically, you just read in the chart. When it comes to exam, the professor will give you some data. In it is the energy of the formation inside of this or this or this, and then you can just calculate it by the summation over here in the products minus the summation of energy of enthalpy formation in the product in the reactants. I'm sorry. So this is the shown of Hess law. You should be very familiar. Okay, so as for enthalpy, entropy, and Gibbs free energy, I think this can be mentioned over here. So okay, over here, like these are state functions. Again, we reviewed that work and heat are not state function, but enthalpy, internal energy, and Gibbs free energy or entropy. And if you are a chemistry student or chemical engineering student in your sophomore year or your junior year, when you study more complicate about thermodynamics, you will learn a new free energy which calls Helmholtz free energy, but it will not be in the content of general chemistry. So how to calculate it? The overall enthalpy change in the reactions. Okay, let's take a look over here. The summation in the products minus by the summation of the energy formation and formational energy in the reactants. So over here, H, the overall is 2 multiplied by negative 46. That's, we look at the chart over here. And all of here, this formation is 0, 0. So it can be like this. Okay, the rest of part of problem, I will leave it to you because it's easy enough, and I don't think it requires so many explanations. Okay, so the next video we'll be talking about entropy and some more complicated working chemical energy changing problems, which okay, that's all.